So here we go. So we talk about rate law. We talk about rate law. It's experimentally derived formula. It always looks the same, okay? Meaning we have the rate which is based upon a speed or a time. So it's basically molarity per time period. That could be second, that could be minute, okay? It doesn't matter, but it really relates to the appearance of products or the disappearance of reactants. How fast they disappear or how fast we make products. All right, we've talked about the implications of delta G and S and all that already. This, of course, is talking about a pathway. All right, any case, that being said, so this is an experimentally driven reaction that, and understand that this formula is based upon, hey, there's brackets there. That's called concentration, that's a molarity. And what we're really asking is, what is the exact speed of the reaction at an exact moment that we know that concentration? It's an initial. Because if I draw a basic curve, okay, where this is the concentration of my reactants, in this case it's XY, over time, we're going to do something like that, okay? And we're talking about, hey, at this point, when I have 100% of XY, what is exactly that rate? And of course, you're looking at me decreasing. I could certainly do this in terms of the production of XY, right? Okay, so that's what we're looking at. We know that over time, the amount of XY is going to decrease. As soon as XY reacts, there's less of it, so over time, this is going to belly out, okay? Now, if it reaches equilibrium, it levels out. So what we're always talking about is the exact moment in time. So if I know, hey, what would be the exact rate when this is lower, okay, at a certain time period, all right? We'll talk about that this weekend, but the point is we're talking about initial concentrations. Don't get lost in how fast does a reaction go if I've got that many reactants at that initial time zero point, which by the way, of course, is your y-intercept, okay? And we'll talk more about the other points in the graph when we talk about calculus this weekend a little bit. But in any case, the important step here is that we're dealing with elementary reactions and non-elementary reactions. Now, what's an elementary reaction? An elementary reaction is a single-step reaction. Hey, the most easiest one to think about probably is not the one I have up here, but I started with this one. The easiest one to think about, I don't know where my tennis spheres have gone, but the easiest one to think about is that I have two particles that collide to make one. It's kind of like the opposite of the one I just drew here, so we're going in the reverse. Hey, two particles independently, now they collide effectively to make one. That's a single step. And as we talked about already, if two things are coming together to make one, all right, in this case is X and Y. Make this X and Y, they're different chemicals. I know the spheres look similar. But if I double this and keep this constant, of course we have many of them, this will find this one twice as fast. So the coefficients equal the order. Keeping Y constant and I double the number of X's, X's will collide more. The factor we're the factor we're talking about in our reaction rate is how many particles do we have. We're not talking about surface area, temperature, pressure, okay, or even a catalyst yet, sort of. Okay, so understand that. All right, now, given that, let's continue. So if I've got what I think is an elementary step, this could be one thing breaking apart. That could be an elementary step. I don't know if it's an elementary step unless I do what? And this is important. I must look at experimental evidence. We can never look at a written formula and say, hey, that is definitely elementary. It's definitely just one step. All right? We have to look at the evidence to support the idea because we can't see them happening, although we're getting to the point where we're all looking at reactions. So here's an example of the experiment, okay? Just to see. And what we do, and I call this the eyeball method. Okay? Meaning what? Meaning that in this case it's just XY. So when I triple the initial concentration of XY in my reaction vessel, the rate of the initial rate also triples. 0.2 times 3, okay, gives me, that should be 6. Okay, I gotta fix that. Okay, that should be 0.6. I found another error. All right, bye. So just trust me, that's supposed to be 0.6. It will be changing. So I tripled this, and I should have tripled that correctly. Let's pretend that I'm a princess, and that's correct. Any case, so what we just found is because they are all the same, the power is killing me. The power, I give the rate law a power of 1. If I tripled the initial concentration and tripled the rate, hey, the power of 1 is just that. Anything to the power of 1, I think I did this right, is just that number. Okay? So I call that the power of 1. The rate is the power of 1 of the change of 1. So, hey, I just figured out, based on this, xy should have a coefficient of 1. And so what does the experimental evidence suggest? That that's my rate law. And hey, that's the coefficient, so it gives me some evidence that that could be a one-step reaction. We never know for sure. Hey, here's a new bimolecular one, or at least this is called bimolecular. That was unimolecular. And unimolecular is easy to understand when you have like a radioactive element decaying. Okay? Any case, here we go. So here's my x and y coming together. Is this elementary? Well, it makes sense that it could be. One thing colliding. But we've got to go to the what? Data. Hopefully I did this one correctly. All right. And so here I have x and y. And again, best way to do this, eyeball method. All right. Now, there is a way, and I showed you yesterday, if they set the data up so that you have to calculate it. And I showed you that, I think, yesterday. You're not going to see that today, I don't think. Maybe, who knows? All right, in any case, what we have is, let's take experiment 1 and 2. All right, let's be crazy and do, 1 and 2. So when I do experiment 1 and 2, I'm going to keep y constant. I didn't have to do that before because I just had 1. So when I keep y constant, that's my control, and I double x, hey, I double the rate, did that right. And so therefore I get a power of 1 for the x, because whatever I did to the x to the power of 1 is the same as the rate. And that gave me what? Experimental evidence that there could be a coefficient just for the x there. Now when we do experiment 1 and 3, keeping x constant with respect to y, hey, y doubled, hey, this doubled. So they both get a power of 1 because the rate is the power of 1 of the concentration change of x. So what do I get overall? I get overall R equals K 1 to 1. And so the experimental evidence suggests that that 1 is because of that coefficient of 1x and 1y, and therefore that rate law suggests that the reaction that we studied was actually just a single step. If this is a single step and I double y, y is going to find x twice as fast. That's why it works. Yes?
But why would it change the power of 1 if it's double?
Because if I double y, now think with me for a second. We have a bunch of y's. Why? Because that's what I'm using. Okay? So if I've got a bunch of y's here, and I have a bunch of x's in my reaction vessel, okay? Now, keeping x constant, if I double the amount of y's, and they're moving randomly, won't y find x twice as fast? So the rate increases. I know in this example we run out of the reaction very quickly, but that's just very simple. So doubling y, okay, means that keeping x constant, y's now outnumber the x's. They're going to find and collide with the x faster, twice as fast, if I keep x constant. So doubling y leads to the reaction rate being twice as fast. Hey, doubling, doubling. Okay, they did the same, which means it has to go to the first power. That's why. Sorry. Okay, moving forward. Now let's go on to something called termolecular. Now a lot of reactions are not x and y. If you look at this reaction, I know it's x and y, but look at this. 2x plus y equals x squared y. And I had a lot of errors when I showed this first period, and I didn't find the other one. Okay, but hey, it's all process. So look at this reaction. This is called termolecular. And it's very hard to believe that this could be a single elementary step. Why? Because as written, I would need what? 2 x's and a y doing what? Yeah, they all got to collide at the same time. The chances of that occurring, to me, just aren't reasonable, okay, on a high level. Could it occur? Sure. But gosh, 3 things collide into 1, that to me is unreasonable. But we don't know until we test it. So You have to test it. Everything in rate law is based upon experimental evidence. You cannot look at a chemical reaction and make any determination. We don't do coefficients become exponents in terms of what? This is not equilibrium. We're saying that the coefficients become orders. Don't confuse yourself. But the coefficients do become the orders if this is a single step. If I have twice the amount of x, won't it find y, in this case, 4 times as much? Because it's already twice. And that would lead to, if that's true. In any case, we've got to go to the experiment. So let's look at the experiment that was done. Okay. We're going to keep, let's see, what did I do first? Okay, yeah. So we're going to keep y constant. So we look at experiment 1 and 3. Here's the eyeball test. Okay. And then I did what? Doubled the initial concentration of x. And this went from 3 to 12. If I did this correct, then this quadruple times by 4. And this doubled. Whoa! The rate went up 4 times. This went up 2 times. Isn't 4 the result of squaring a 2? So this, by the eyeball method, okay, this means that the rate is equal to k plus the change here squared. Power of 2 here. What if this went up 3 times? And this increased 9 times, you would still get a power of 2. So the rate changed by the square of the change of the what? Initial constant with respect to x only, keeping this constant. Hey, we got somewhere today. Good, I love that when I see the aha. All right, so this tells me by the eyeball method, and I'm telling you, on the test, you can just do this. Now, there are times where you have to do the mathematics. You say, well, how do I know if I have to do mathematics? I would take experiment 3 and divide it by experiment 2. And did I pull this out yesterday? Did I show you this?
I think so.
Okay, but for those that don't see it, and I want to show for those that didn't see it in other class, so I'm going to compare. I know we can do the math in our head here, but if I do experiment 3 over, and I'm always going to do the bigger one, over what? Experiment 1. I'll say, so number 3 over number 1. And so rate equals what? K. We have what? X, whatever x is, and whatever y is. Remember, it's 2x. Who cares? We don't know yet. So this is the concentrations. Okay? So same thing. Rate equals K, x, and y. Now, what we know, okay, is this is M, N, and N. Okay, so in any case, the rate of number 3 is 12. Okay, remember this is divide by, right? Okay, rate of 1 is 3. I'm gonna need help, that's for sure. Okay, hey, the K's are gonna be the same. This constant is a constant because it stays the same. Put in the values of y. Well, y will be 0.16, 0.16, right? And these orders, whatever it is, will be the same number, so that's going to cancel. All right, now put in the values of x for 3, 0.5. I know this is silly, but if you see numbers that you can't identify with your eyeball test, you can just do the math. And this is what? 0.25. And so what you get is 12 divided by 3, and you can find that number. And it may not be clear to you if it's a weird number that you can't do in your head, but in this case it comes out to be 4, and it will be a whole number when you do it, even if the number looks like 0.0185 over some number you don't know. And that'll equal to what? That equals to, this is the same number, right? So what does this mean? 0.5 to what? I'm sorry. 0.5 divided by over 2.5, isn't that a 2? 2 to what number? N. So what squared equals 4, and you get 2. And you say, Mr. Grodsky, why did we spend all that time? Because sometimes this number won't be 1 to 1. It could be 0.16 and 0.28 or something, and you'd have to, if you already know that order, you can find that number you're going to solve for. Okay, or these numbers, you can't eyeball them. That's like 10% of the time. Okay, all right, perfect. Now, what do we do for the other one? The other one, okay, check it out. The keeping x constant with respect to y, we're going to double y, whoa, the rate doesn't change. This screams to me, hey, how can that happen? I'm doubling y, keeping x constant. With respect to y, the order of y must be what if there is no change? 0. And anything to the 0 order means, very important, that changing its concentration has no effect on the rate. And anything to the 0 power just goes to 1, which is nothing. It has no effect, so therefore the equation doesn't need any information about y. Okay? Why? Because I used that letter and it stayed what? The rate stayed constant when I made the change. Changing the initial concentration of y had no effect on the initial rate of formation of the products. So party people, from my experiment using the eyeball method, what do I get? I get my two orders to be r equals k to the x squared. The eyeball method gives me this, and I'm telling you, you can do it fast. All right, and sometimes they just want the order. Sometimes they say, give me an explanation. You can say in reaction 1, I'm doubling. You can just go through that. You don't have to show that. But you may need this, okay, if the numbers aren't clear to you and you can't eyeball it. Okay, also I can write it this way as well because this goes to 1. Okay, so there you go. Now the question is, was this a single step? Well, wait a minute, if it's a single step, this 2 would go here, good. But I should have a 1 for my y. Ooh, the orders don't match the coefficients, which screams to me that this had to occur in something called a reaction mechanism. Okay, so what does that mean? A reaction mechanism is a bunch of steps. Most reactions do not occur in a single elementary step. Most reactions occur, and you saw that with Hess law, when you were manipulating equations, you can do that. Most reactions occur in multiple steps called a mechanism, but we can't watch them occur. So people propose mechanisms. This is a huge part of chemistry. If you're into biology or pharmaceuticals or biochemistry, if you learn about biology, remember that whoever your biology teacher, I hope it was good, talk to you about the transduction pathway, where there's a reception and a cascading of signals in the cell that lead to a cell response. And there's many steps along the way that we can regulate. Well, guess what? Those many steps are steps in a reaction mechanism that pharmaceuticals try to jump in and try to manipulate to stop or start a process. Very interesting. Okay, now, so someone just proposed a possible mechanism. Hey, I think that this might be the series of steps that I want to understand. So someone proposes this, and you need to understand there's 2 ways. Okay, it was in your homework last night, it might not have been clear, but there's 2 ways to identify whether a mechanism is correct. The first one's the easiest. Does this series of steps cancel out to the overall reaction? That's the first thing. You just said, really? Yeah, they'll ask you, give me a couple of reasons or one reason why this mechanism could be. It's always could. You never know exactly. Could be correct. The first one is, does it cancel out? So when we cancel, okay, does it cancel out? And it sure does. So this could be. Okay, now, let me take a step back. So the first thing, to test the mechanism, does the mechanism actually cancel out the overall reaction? And it does, okay? Now the second and skill that's built into here, and you need to understand this, is to identify the parts of a mechanism. Okay, so there's kind of 3 skills involved here. Okay, so let's look at a mechanism. We know that it overall gives me that, but I have color-coded these because it's realized. These are my reactants, and this is my product. It took 3 steps to make them in this chemist's proposed mechanism. Now, you need to identify the parts, because in order to do that, the second part helps you. This is called an intermediate. This plus a chemical made an intermediate. Intermediates are extremely reactive. We can't really measure them because as soon as they're made, boom, they react. So these guys are intermediates. What's special about intermediates, they link one step to another, okay? And so it's important to realize that, hey, I produce something, hey, that something is creating the second step. That's an intermediate. So they'll ask you on an AP test, where are the intermediates? And hey, they get produced, and they link one step to another. So there's 2 intermediates here. But notice there's another chemical that's not being produced, starting as in the reactant side, but being reproduced. That, my friends, is a catalyst. And you probably learned in an earlier science course, catalysts never get consumed in a reaction. Here is the reason why. A catalyst starts a whole series of these steps, or I should say the catalyst is responsible for this mechanism. This is an example of a catalyst-driven mechanism. I add Z, I create these series of steps because I just created this intermediate. Without Z, this doesn't occur, doesn't it? No. So I'm trying to teach you something. Yesterday I did the elephant's toothpaste. The decomposition of hydrogen peroxide stood there until I dropped some iodine ions. Iodine ions were a catalyst. And I added them to the reactant, and they were reproduced, and what did they do? They made an intermediate for the second step to occur. So you have to realize that this is a catalyst, and it'll come up. You have to add it to one of the reactants to create the mechanism. Now, what do we learn about? And this is important too. We're going to talk about this right now, okay, as Van Halen would say. All right? I think it was the 80s, okay? So, any case, here is my potential energy diagram of the overall. Let's just assume it's exothermic. And we all know what? This is the phase zone, right? Okay, now, we're not changing delta H, are we? Delta H is negative, we should know that. It's going down. It's a spontaneous reaction, delta G is negative, but this is my E of A. This is my energy barrier. Okay, we learned, you guys learned that a catalyst lowers the activation energy. But how does it do that? It does it because it starts a whole series of reactions that collectively has a lower activation. So these are three reactions, right? So let me draw them. Yeah. One might be endo, one might be exo. But if I measure these three activation energies and I add them together, the collective activation energies of those three steps is what? Less than the activation energy of the one step. So these three steps collectively find an alternative pathway. Who created this pathway? The catalyst. So when you answer a question about what catalysts do, the best answer is alternative pathway. Yes, it lowers E of A, but you should understand it collectively does. That's so cool. All right. So intermediates get produced and then start another reactant. Guess what? The catalyst is what creates this whole series of steps. Without Z, you don't have this pathway. That's why without Z, you don't have this lower pathway. I hope you get that. Now, we already found that this cancels out to the overall. That's one way to say that this could be. The other one now is, most importantly, does those series of steps lead to the rate order? What's the rate? What were the rates? We got it. X to the 2, y to the 0. We've got to see if that does. So what we do is we have to use some analysis. Let's go back to our analysis here. Okay, now, if you notice, I got the first one as the slowest step. Sometimes on the test, they'll tell you which step is slow and fast. Okay, but sometimes they don't. So here is my analysis here. Now, how did I get to this point? Well, think with me for a second. Intermediates are classically what? Extremely reactive. It's hard to measure. They're not in the rate law because you can't measure them. So think with me for a second. This being highly reactive, this X is waiting for a highly reactive molecule to what? To appear. Now once it appears, boom, it's fast because it's reactive. What did it make? Another intermediate. And this Y, as soon as it's made, reacts fast. But both of these reactions are dependent upon the first intermediate being made. So these two are extremely fast, but this one, X is waiting for XZ to be made. And this one's waiting for X2 to be made. Because of that analysis, it must be that these two reactions, or this entire process, is as fast as we make XZ. This must be my slowest step, because I'm making intermediates who are highly reactive. But X and Y in the second and third step are waiting on one, as I said yesterday, to get out of my house. Okay, we're as fast going somewhere as a family as the slowest person who leaves the house. Okay? When I was growing up, you just got left. So things have changed over time. Right? Now, so this is my slowest step. And I call the slowest step the rate determining step. These two faster steps, although they're faster, are waiting on it. So the entire process is as fast, and this is the key, to this intermediate step. That's the key. So this is the intermediate step. I'm sorry, this is the elementary step. That's key here. Why? What do we know about elementary step? These steps that are in the mechanism are always elementary. And what do we know about an elementary step? If we want the rate law of the elementary step, what do? Coefficients become the orders. So what is the rate law for that elementary step? Notice I don't put the what? Even though I did it in my homework, Bad Grodsky. Don't put the catalyst because the catalyst gets canceled off. So we get from this proposed mechanism k to the x1. But wait a minute. My evidence gives me this. Is this mechanism appropriate for the experimental evidence? We get this experimentally from the evidence, we get this from the mechanism. Does it match? No. So that's not an appropriate mechanism. Okay, I drew another one. This is mechanism 2. You can guess that this one's correct. Now, how's this one different? Well, first, does it cancel off to give you the overall? Yes, that's the first check. The second thing is, does it give me a rate order, most importantly, that matches my experimental evidence? Now, before we get to that, how is this one different? Okay, which one is my catalyst? It's a loaded question. There is no catalyst. Because if I had a catalyst, it would be reproduced. This is a mechanism that does not have a catalyst. So this one, but it does still suggest that I make an intermediate, highly reactive intermediate. So if this is a highly reactive intermediate, this one must be what? A fast reaction. But it's only as fast as the making of the intermediate of step 1. So the whole process is limited by how slow this goes, and this must be my slowest rate determining step. And therefore, because this is an individual elementary step, what do we know? Coefficients become the order. 2x gives me x squared. This gives me what? R equals k. And I don't have it here because I didn't finish. So what it gives me is R equals k, x to the what power? And I don't have any y, do I? So y is 0. Hey, this mechanism supports the evidence for 2 reasons. Overall, we get the correct reaction, and 2, we get the rate orders. Yes?
Is the rate determined? Is that normally the first one?
It is in this scenario. It's always the slowest one. Now, last night you guys did fast equilibrium. Fast equilibrium, the second one is. Because that one's going, because in if you have a fast equilibrium, I don't know, x plus, oh, it's a plus, x, 2x I should say, going to x squared. If you're going back and forth, think with me for a second. Let's do x squared plus something. Let's do one of the plus y to make y x and kicking out an x here. Okay, who cares? The point is that if I have fast equilibrium, this step is waiting for the possibility. Remember, here's y. So I have 2x plus y is my 2 reactants. Are you with me? Now listen, very simple. If I have a fast equilibrium, as soon as 2x makes x2, x2 goes back to make 2x. So that means that x2 isn't around long enough. Hey, I'm a y, and I want to collide with an x2 to make the second step happen and finish out my mechanism. Oh, and I see an x2 appear, and I'm going for it. Now, of course, it's just random motion. And as soon as I get to it, it becomes what? 2x. So this y is waiting, really, for the availability of enough x2s to collide with it. Because x2 goes back, it's not there long enough. So even though So this must be my slowest step here. This is the rate determining step, always the second in a fast equilibrium. Because it's got to wait for the availability of the X2, because it goes back so fast. And as you did last night, you can relate the intermediate to the other chemical because of the equilibrium. All right? That you won't see in your test today. So the answer to the question is no. In fast equilibrium, the second's the rate. In the case where you're creating intermediate, it's the first. And a lot of times, guys, if they give you something that's not in between, they'll tell you. If I'm telling you in a multiple step, that one's this, then you take that reaction, coefficients become orders. Boom. Make sure you don't put an intermediate in there or a catalyst, because they cancel. It's only the reactants. Okay? All right. So let's go to some of your homework. Okay? And again, this is all available. All right, for your viewing displeasures. Not that you need it, maybe you do, I don't know. Some other people might. Okay, so party people, let's go back to our week here. I think it's 7? Yeah, and we're Freitag, Friday. Good times. What am I doing? Okay. 48 days and counting. All right, now, so let's go to, hey, did you run through some of these? Hey, this one right here was cool. This I did the same reaction, but in a smaller neck volumetric flask. This shot to the roof. Okay, all right. Hey, good times. We used a much bigger one. It wasn't as sexy, but it's okay. Any case, so back to reality, and let's do, the homework was complete kinetics, fast equilibrium. We did that last night. First page, 1984. Okay, so that's the packet, and that would be right here, I think. Did we do this one?
Yeah.
Okay. Oh, so, yeah, here's a great example. So, sorry if I didn't mention this yesterday. This is me doing what? The eyeball method. This is the non-eyeball method, which was not necessary. Unless you couldn't see that that 2.8 times 10 negative 3, okay, wasn't really 28 times 10 to the negative 4, right? This is actually 4 times that, so if you didn't see that, you could have put that in your calculator. But any case, this is not what I want you to do. You don't have time. Anytime you can just eyeball it and do it, or you're under duress. See, the thing is, some of your questions you do on your part 2s take a lot of time, right? Sometimes the thermo is like, oh my God, find a delta H, and you got to do all these bond energies and negative signs. This is where you get to save time, okay? Kinetics or rate laws are fast, really fast questions. So none of this. This would take 10, 15 minutes to write this out. Yes?
So like if they're asking you to like I feel like for
If they ask for support,
yeah.
okay, you can quickly say, look, you could say keeping something constant, the rate was, and you can write 28 times 10 negative 4 over, that equals 4 times. And you can quickly jot down, that's the square. The rate was the square of the change of the reactants. You can quickly say that. This takes too much time, okay? So if they say give support, say, hey, listen, I kept X constant, Y doubled, my rate quadrupled, and I showed them 2.8 times 10 to the 3 divided by 7 by 4 equals 4, and the square of 2 was 4. Boom, okay? Do put some words there. Don't just show math, because sometimes they don't think that you know what the math means, okay? That was not necessary. Okay, this is a skill you must have. The rate constant. Knowing this is 0, this goes to 1. What did I do here? Okay, I put the rate, I solve for K, just rearrange this, right? Solve for K, this goes to 1. So K is the rate over what? Y to the 1 power. Don't forget units. Now, I'm going to tell you right now, I did moles over liters. Don't do that. Don't confuse yourself. Okay, I really should just do molarity. It should be molarity per second. And it's important because they do what? Units count. Molarity per second over what? Okay, molarity. Now why? Because rate is molarity per second of the disappearance of the reactant or the appearance of the product. This is to the first power. So you should be able to see that really this is the same thing. Molarity over molarity second. It's the same thing. So boom. What are you left with? 1/2. You can do this, or you can do this. So in this case, okay, the units were seconds to -1, and that will be its own point. Now let's just pretend I'm a princess, and it was squared, and I solve for R. Hey, that's molarity what? Squared. I still get rid of that, but the squared becomes 1. I have one molarity, so it would be what? 1/molarity second, which is the same thing as saying molarity to -1, second to the -1. You must calculate every time. That's going to be 2 points. 2 points today. We don't have this yet. We don't have this yet. Hey, look at E. So which mechanism is most appropriate? Okay? Now, they could ask you, now we did this yesterday, but hey, they told you who was slow. Okay? So the slow, hey, the orders become the what? Exponents. 1 to 1. But what did we get? Didn't we get Y? Who was 0? Y? So this wouldn't work. This one, here's my intermediate. Notice the fast one, they're telling it's this one. Okay? And we get a 1. Y is 1, and there's no X here. And then the third one, okay, hey, who's slow? There's just Y. Y to 1. And because X was not in the slowest step, it gets a 0. So that's why 3. Any problems there? No. What was the other question we had for homework?
1990.
This one, right? Ah, this one was your what? Your fast equilibrium problem.
I think it's big.
Is it not this one?
No.
Okay, my bad. Or am I good? Oh, it's this one. Okay. The following sequence of elementary steps is a proposed mechanism for the reaction. How about I just do this one for you to make you feel better? We're not going to do. You're not going to see this today. You'll see it Tuesday. But I want to do this for you. I'll give you the break after I just do this. So I want to answer this. Okay. Now, same thing. You notice you always seem to be starting with what? Experimental evidence. Okay. All right. Now, am I thinking that one you had to calculate? I forget. All right. Now, let's start. I want to give this to you. Because you had me do it for the other two, let me show you what I'm doing here. Okay? So, here are the 3 steps. 2 no's equals a yes. NO plus NO gives me N2O2. And that's the fast equilibrium. Okay? How do I know? Arrow is screaming to me. Okay, then I get N2O2, which is my intermediate, right? Plus H2. All right, gives me the water. Plus N2O. And then I got, N2O. Another intermediate, right? Reacts with H2. Gives me N2 plus H2O. Okay, what are they asking for? Based on the data presented, which above is the rate determining step? Show that the mechanism is consistent with 2. Okay. Which above is the rate determining step? The rate determining step is going to be this one. But they want to do 2 things. Based on the data, the observed rate law for the reaction, the overall stoichiometry reaction. Know what this is asking for number 2? Does the whole thing cancel out? That's one of the ways to do this. Let's cancel out first. Now they're not asking it here, but I could ask it, hint, hint. Okay, what am I going to cancel out? Well, I'm going to cancel out intermediates, right? Who are my intermediates? Sounds like idiots. Okay? Hey, this one links this step. Hey, this produced another intermediate, yes? And notice they're both on the same side, so booyah, my intermediates go bye-bye. Now, interesting enough, the NO doesn't get reproduced, the H2 doesn't get reproduced. There are no catalysts here, right? This is not a catalyst driven. Okay, let's write the whole thing together. So we got 2 NOs plus what? Do I have any H2s?
Yeah, 2 H2s.
Okay, plus 2 H2s. Give me an N2 plus H2O.
2H.
Oh, 2 H2Os, yep. Hey, that's a point. Now they're saying overall stoichiometry. That's a point. Or they could say prove by one method that this could be. That's one way you do it. That's one point. Come on, it's easy. Okay, the observed law for the reaction. Okay, in the way to prove the observed law, what we're going to have to do is we're going to have to prove this out. Okay, so I'm going to get rid of this. Okay, and there's many faster ways, but we're going to have to prove that this is the rate determining step. Okay? Okay, now, watch how I do this. Okay, now, this goes back and forth. This is waiting on it. Okay, oops. This is the rate determining step, my bad. In a fast equilibrium, as we said before, H2 is waiting on this to be what? Available enough to go forward. Since this makes N2 and quickly does what? Goes back, this H2 can't find that. Right? So this is waiting, okay, for this to be available. So this is my slow step. This is a fast step. And because this H2 is waiting for the what? A second intermediate that is what? Produced by the second step, who is waiting for that to be available and not go back. Clearly, this has to be not as slow, but it could be what? It's not the rate determining step. But basically, this step is waiting, okay, for this to go. So the bottleneck in my reaction is right here. And that's my rate determining step. Who does not understand that? This third step is waiting for the production of N2O2. And this step is waiting for N2O2 to be what? There long enough to hit, so my slowest step, and it always in a fast equilibrium, must be here. Okay, but now we gotta prove that the reaction, what? Orders I get from my experiment match. So, here's my problem. This is my elementary step, right? So, R equals K. Now this is K of the second step. Okay? Times the what? Concentration of N2O2 times the concentration of H2. Now you may say, well, I can't put an intermediate in here. You're right, I can't. An intermediate is not part of the reaction. But I'm going to use it to relate to the other reactions. If you just took this away and made this one, you'd be wrong. Here's the reasoning. As fast as N2 is what? Made is the same speed in which the two NOs go forward. What do you know about equilibrium? The rate of the forward equals the rate of the reverse. That's the link. So as fast as this is made is the same speed in which this is reacted. I'm going to use that. So what I'm going to do is I'm going to solve for this. This is a reactant. I'm going to solve for this. Okay, so let's go to the first. So let's go find N2. Let's go with what do we know? We know that the rate of the first step is equal to what? K of the forward times what? It's an elementary step, isn't it? So it's NO to the what power? 2. I don't need this anymore, but it's equal to what? The rate of the reverse, which is equal to K of the reverse of the first step, and that's equal to what? Yeah, let me rewrite this for those that can't see. So the rate of the first of the forward equals the rate of the first of the reverse. So party people, of the forward reaction, I've got K forward of the first, okay, times NO squared, and that equals the K of the reverse of the first, and that is N2O2. I want to solve for N2O2. So when I solve for N2O2, I'm going to divide by KR1, which is the reverse equilibrium constant for the first step. Just doing what? Algebra. And there I go, party people. I have an equivalent of this intermediate that's linked by what? Fast equilibrium. And so when I plug this in, just stay with me. When I plug this in here, what do I get? I got K2 times KF1 over K reverse 1, okay, times NO squared. Put this back in, because it's just, we're plugging that in to this position here. H2, Christmas. And what's cool about this is, oh, what's this mess here? Well, the actual K of the reaction. The rate law constant for the second times this fraction of the first just winds up being, whatever that value is the K of the entire reaction. And there is your rate law based upon this mechanism, only with fast equilibrium. Not going to happen today's quiz. So you need to show quickly to relate this intermediate back to this original. I don't think it, we do it a couple of times, okay, it doesn't look so crazy, it's just some math. These are equal, okay? So solve for it. Then plug it in and realize that the K is just the K of the reaction, all right? Any questions? Okay? All right, we're gonna take a test. I don't hear yay. The energy in here is incredible. Didn't make too many mistakes.